Space, the final frontier, the ultimate limit for explorers. And where no man can boldly go, we've sent robots. Robots, drills and scoops to sample the secrets of our nearest neighbors, beyond the moon to Mars and Venus. But even more extraordinary will be to sample a comet, because comets might have brought vital ingredients for life to Earth. Now there's a unique opportunity. In 2012, a comet will speed through the far reaches of the solar system, and there's a plan to land a robot on it. This robotic drill must be smaller and lighter and operate further from Earth than ever before. The rewards could be huge, perhaps a clue to the origins of life itself. There is a competition to design the robot drill. Two men are leading it. One is a New Yorker, Stephen Gorovan. Gorovan is the new boy of the competition. He has been working on the comet drill for just a year.
This is what the surface of a comet might look like, and the lander may land right on that. Well, that's what we're going to find out, Casey. We're going to drill a hole in that comet, and we're going to try to find out what's inside there.
Just exactly how are you going to do that?
That's a good question.
5,000 miles away in Milan, Gorovan's main rival in the competition is Mauro Fenzi. He has a head start, having already spent 7 years developing ideas for the comet drill. He works for the European leaders in robot technology, an offshoot of engineering giant Fiat.
If I will succeed in this kind of development, I will fulfill one of my dreams, to leave something for the future behind me, to be then useful for the overall community. So really, my 20 years of developments really will have an importance, not only for me.
The competing designs will be judged by NASA in 6 months' time. For Gorovan and his small company in downtown Manhattan, it's the opportunity of a lifetime.
If the mission succeeds, and it turns out that the work that myself and the engineers that work with me has been important in achieving that goal, then it's a fantastic possibility, because we will have the opportunity to achieve a small slice of immortality. I believe the mission is that important.
It's only 9 years since a spacecraft first came close to a comet. In 1986, Giotto saw the tiny, craggy nucleus of Halley's Comet.
People watched and wondered, not quite believing their eyes. For the first time, they could see the comet's nucleus at so close a distance.
Just a few kilometers wide, a comet nucleus became the target of a new mission, Rosetta. Due to leave Earth in 2003, Rosetta will take 9 years to catch up with comet Virtanen. Circling through our solar system, it will travel 600 million kilometers to the far side of the Sun. When it finally arrives in 2012, a lander will be ejected onto the comet, and then a robot drill will take samples. Because it's so far away and no one knows what it's made of, the drill that's chosen to make this voyage will need to be a miracle of engineering.
My impression has always been that most finished engineering devices or achievements are arrived at in small increments. And now, with the Rosetta Cometary sample acquisition system, I believe that we have to arrive at it in a humongous increment. That is to say, when you first hear about what it has to do, the first requirement is, well, we've got to go down a meter and get a sample. Okay, that's not so bad. Second, you've got to be able to go down inside of the comet and get the sample, but you really shouldn't have the thing weigh more than 2 kilograms, and it shouldn't use more than 5 watts at any given time. And, you know, our jaws are starting to drop at this point. And when we ask, what is the comet made out of, they said that, well, it could be anything that's sort of akin to shaving cream all the way through to rock-hard ice. So it turns out that the robot has to be able to drill into and handle those two extremes and everything in between.
The first challenge was to find something to test drills in. As the toughest, coldest stuff Gorovan can buy off the shelf is ice, it seemed a good place to start.
I need a block of dry ice so big.
The dry ice test that we performed was one of the first things we did.
What do you need to dry ice for?
Well, well, if you really must know, I'm trying to drill a hole practice drilling a hole in a comet.
You drill a hole in a comet?
Yeah, well, somebody's got to do it.
We knew that the comet, it was not likely to be a hunk of dry ice, but we thought that we needed something quick and easy that would be somewhere maybe in the ballpark as far as drilling purposes are concerned.
Let's start the clock. Go ahead.
Ready now.
We had our own custom drill bits, augers, shearing devices, all kinds of things that we wanted to try.
Give it another 20 seconds.
The drill bit is the most important part of the robot, but finding one that will work isn't easy.
It's not just a question of drilling into ice. With this hand drill, we'll probably go down an inch and consume 100 watts. For the mission, we'll have to drill down 20 centimeters and consume less than 5 watts.
Over in Milan, just like his local hero, Leonardo da Vinci, Fenzi is trying to solve problems for a future and unknown world. For the past 7 years, he's been working on earlier Rosetta plans, which are for a much bigger spacecraft and drill. Despite the decision to miniaturize the mission, Fenzi is still working big scale. His challenge will be to shrink his drill down.
One thing I'm very worried about is to find on the comet some stones. What we are trying to do is to design a driller able to move away the stones. Because if you try to cut this kind of stone, you can have a failure of the drilling operation.
While Fenzi works large scale, Gorovan has one advantage. He's worked on tiny robots for years. The latest was for a cancelled mission to Mars.
This outer tube and assembly would be connected to a lander. And imagine we've landed on Mars, and here's the surface. And upon giving a command to drill, this reel will start to move and lower the sample acquisition probe towards the surface. One of the best things we learned about our Mars sampler was miniaturization. And this, of course, is crucial to the Rosetta sampler as well.
The soil gathering device was now brought into play.
Robot sampling in space has already had a long history. The first ever planetary drill was sent by the Russians to the moon in 1970. It was a bulky and power-hungry device. In 1981, after 11 disastrous attempts, the Russians sent a lander to sample Venus. It too was heavy, weighing in at a massive 28 kilograms. These probes relied on their weight to drill into the planets. The comet presents the competitors with a totally new drilling problem.
We can't use the Mars sampler because it was completely dependent on local gravity to function. On a comet, we have virtually no
gravity to work with, so the Martian sampler is not applicable.
A comet is so small it has hardly any gravity. If a person were to jump up on one, they just fly off into space. Even with legs to grip the surface, the lander will have a job holding on.
Here's the comet surface, here's the lander. We're in a zero gravity and going into something we're not even sure what it is. Here's the drill, we're thrusting down, and it may be that this small thrusting force will overcome the hold of the landing legs, and we have the lander popping off the surface. And so we have to come up with a drill that requires as little thrust as possible.
Instead of being pushed down, this drill will somehow have to pull itself down.
In the beginning, every means of penetration was looked at. In the end, it came down to an augering technique because it worked best. Just as a corkscrew goes into the cork through a twisting motion, you actually put very little thrust into a corkscrew. We're looking for the same thing with this drill. We're looking to have an augering effect pull us down into the cometary material.
But a corkscrew relies on someone having a good grip on the bottle. In unknown material and near zero gravity, no one knows how well the landed legs will grip the comet.
The problem we have to solve is that the auger will generate a torque or twisting that has going to be reacted into the lander, but we've got to make that as low as possible or we could set the whole spacecraft spinning.
After weeks of testing, Gorovin's team think they've solved the first problem and found the ideal drill bit.
This is the high helix single fluted auger that worked really well in dry ice, and this one, on the other hand,
The one that worked well because the angle of attack was just right, so that it seemed to give us just the right augering effect and require only a little bit of thrust, certainly below the 1 kilogram.
In Italy, Fenzi has been testing huge industrial augers. Even scaled down, they'll be tougher than Gorovin's because Fenzi believes the comet will be harder than mere ice.
Scientists have different opinions on the cometary environment, and European scientists are more focused on medium hard material. American scientists are more in favor of soft material to increase the level of success of the mission. We decided to focus the attention on the hard material to be ready in the worst case on the comet.
On a personal level, I can have vast stretches of time when I don't even think about anything to do with my work. I'm spending time with my wife and children.
Hey, Molly Joe, you have any idea of where we're going?
No.
Can you guess?
I'll be going over the moon. Dole, Rockefeller Center.
Yes, we're going ice skating. That's it. You just keep smiling. And you'll be...
It's kind of like having a fit or something. Every once in a while, something bubbles up in me that's been triggered by something I've been doing with my children, and I'll start drifting off and thinking about the sampler. And other times, I can't even tell why I all of a sudden start thinking about it. I just find myself thinking about it a lot. I just want to make it go.
To make it go, Gorovin now wants to test his drill in something harder and colder than ice. He's experimenting with a frozen rock cocktail, a sort of pretend comet that NASA have sent him.
Speed.
10 centimeters. 1.5 inch thumb.
I think the most exciting thing that's happened so far is that, given the cometary analog that we've worked on, we were able to successfully drill down a meter. This was a very surprising and happy result.
Still at 1 inch.
Fenzi still hasn't tested anything tiny. He's designed a drill with a very large center and diamond-tipped teeth to cope with the tough comet he expects. his drill bit has a final frozen test in liquid nitrogen. Designing the drill bit is only the first problem. Controlling it is another huge challenge. At 600 million kilometers away, each command from mission control would take half an hour to reach the comet. Sampling the unknown, the drill will have to react moment by moment. So the engineer must give it intelligence to control itself.
The way we give the sampler a flexible means of being able to deal with a vast array of possible conditions is through the use of the 3 onboard sensors and the program written to interpret the information coming from these 3 sensors.
When it lands on the comet, the drill will be sent down from the middle of the lander. If it finds hard material, the corkscrew effect will pull it in. If it twists too much and the lander turns, then a torque sensor will say turn more slowly. If the comet is soft, it would be like trying to turn a corkscrew in whipped cream, and a depth sensor will say the drill is not going down. That will trigger a motor to start pushing. The third sensor checks this motor doesn't push the lander off.
Using these 3 sensors with a program, if that gives it some cleverness, if you will, we're able to deliver a sampling system that can meet any comet they can throw at us. Engineers are lucky if they get to work on a project that demands a great deal of creativity. I used to be involved in music, for example, before I became an engineer, and it strikes me there are a great deal of similarities in the creative aspects that are going into what I'm doing now with respect to the Rosetta mission.
The critical part of the mission will be retrieving the crumb of comet and analyzing it for the secrets it could hold. Many scientists believe that billions of years after the Big Bang, Earth was little more than a barren globe. They say a shower of comets crashed into it, bringing the vital ingredients needed for life itself. Analyzing the sample from the comet nucleus will test this theory. But as we can't bring the sample back, the engineers have a final challenge: to get the sample from the drill to the instruments inside the lander without any control from Earth.
The soil sample has been taken. Now it's in a capsule.
For this part of the mission, it's no use looking to history. The transfer of samples on the Moon used a large device controlled from Earth. On Venus, it was even more elaborate.
Pipelines sucked the soil in and hermetically sealed it.
They were also very complex, too risky for a short mission in an unknown environment. Goravan and Fenzi's design must be simple and completely autonomous. And here their approach differs again.
We go down to the desired drilling depth. Then and only then do we open our sample acquisition cavity. Continued drilling fills the cavity, and at this point we close and seal the sample inside, preventing cross-contamination from material at other depths.
Fenzi again draws on his industrial heritage. He is planning a baby-sized robot arm which will move the samples from the drill to the instruments. But robotic arms are not simple devices, and this may be a problem.
The robotic arm is quite complex. You have a lot of components, sensors, actuators, circuit boards. But if you know from the beginning, because, for example, I'm a specialist of robotics, the functions, the performances of these components, you are very confident in the final performances of your ideas, your robotic ideas.
From what little I've seen of the Italian scheme, I'm struck most not by the means with which they penetrate the comet, as I thought I would be, but their use of, instead of their robotic arms to transfer the sample from the drill, if you will, to the instruments. This intrigues me a great deal. I would have never taken this approach. It's interesting. I'm just wondering if they can really make that lightweight and simple.
As he drills down, Gorovan has an ingeniously simple way of delivering the sample to the instruments. With the sample trapped inside the drill, he simply moves the whole drill over and feeds each instrument, including a tiny microscope, an individual crumb of comet. But if the mission doesn't go according to plan, Fenzi's complex robotic arm could give him the edge.
We are not fully sure about the final position of the lander. The lander can land on one side, for example. In this case, the main driller will not work. What we are proposing is to use the robotic arm for collecting a small sample from the surface of the comet and to bring this small sample to the instruments.
This backup idea could be the thing that swings it for Fenzi, but it's up to the judges at NASA to decide. Los Angeles, home of NASA's research headquarters. It's the day of reckoning. The competitors will have to present their work to the world's top comet scientists. Fenzi arrives jet-lagged from Milan. Gorovan has come overnight from New York. They each have different worries about their proposals.
The nightmare that I'm having now is that during the long cruise phase that lasts for years, that in the middle of it, I've had so much time to think about it that I'm going to wake up one day and say, oh my God, we forgot something.
Fenzi is more nervous about the scientists themselves.
For the meeting of tomorrow, I will be worried because I will have in front of me people involved in space field with a very good background and company is very important. So for me tomorrow will be very difficult, but I have the feeling that we have very good background, mainly gained in the past experiences, really on the field. And it's not quite usual, because only few people in the world already have this kind of background.
At the massive research center, it is Gorovan who has to face the scientists first.
This concept, what we have is a motor and a gearbox driving the auger down below through an internal keyed shaft. This is a high helix, single fluted auger. We thought this would work. It worked in the dry ice, and it worked on the comet analog we were given. It worked quite well, in fact. High torquing on an uneven surface.
Very intimidating being in front of these scientists. It gave me a little bit of a pit in my stomach, trying to give a presentation in a room where you can't see anybody's face and nobody answers a question. You can't tell exactly how it's going.
We did some analysis. We did some ice drilling and the talc penetration test we did for Mars.
Okay.
Fenzi follows and presents ideas, mainly from the old large-scale mission, as he thinks scaling down won't be a problem.
Conceptual designs, of course, just to give you an impression about what they are doing in this frame. First, we started a series of tests on the bit of the corer, which is the critical part of the corer, because has the main function to cut the material with very low loads, so with very low torque and with very low thrust. I believe that our presentation has been successful in the sense that we convince people about the background and the concepts. Sample collected to the different instruments. We estimated the mass of...
The Italians came in with a presentation that was a lot less further on than I thought it could have been. I was very pleased with this because I was worried that they were going to come up with something directly pertinent to the miniaturization required of Rosetta. When your competition doesn't come in with something that really hits hard, it makes me happy.
Fenzi too senses things didn't go well for his team. He thinks the scientists on the judging panel don't really appreciate the engineering challenges.
The only concern that I have is mainly related to the gap that, my point of view, is between technical people that should design the hardware and the scientists. I think this is a point on which we have to work in this next month. So we have to try to fill the gap that is existing between the expectations of the scientists and what we can do technically.
I think they're going to give us the job and we're going to live happily ever after. That's what I think might happen, but you know, I don't know.
Bye-bye.
For the competitors, there's nothing to do but wait. It'll take months for NASA to decide which design they'll choose. Whoever wins will spend the next 8 years perfecting their plans before the launch in 2003. Then a further 9 years anxiously waiting to see if they got it right. For the privilege of pushing the limit of robot design, it'll be the best part of a lifetime's work.
Come on, let's go look at it. Come on. Look.
Will we be the first ones to go there?
We hope to be with the group that will be the first ones to go there.
How old will I be when the machine gets there?
You will have graduated from college, and you will be somewhere close to 24 years old.
Wow, wow, wow.
No, it's going to take a long time for the lander to get there, but actually it's only going to take just a few minutes to drill the hole and take the sample.
And if you'd like more information on engineering, then please telephone 0891 22 11 22.